Okay, our today topic is two degree of freedom system. Before this, for the whole class, in the beginning of class, we talk about how to obtain the equation of motion of some system, maybe one degree of freedom or multi-degree of freedom systems. But in the content of the class, we just focus on the vibration of single degree of freedom system because it's a kind of basic system. But today, we will extend our knowledge from the previous class to apply it on two degree of freedom systems. But two degree of freedom system is a lot more complicated compared to a single DOF system. So yeah, today we just focus on undamped free vibration of second degree of freedom system. First of all, today we will give a short review. How can we obtain equation of motion of second degree of freedom system? And then we will try to imagine about the vibration of two degree of freedom system, and we will have one assumption that we can continue to analyze the vibration. The assumption is based on the observation of system. The assumption is we assume that the system, the motion of the system is synchronous system. Today we will know what is the meaning of synchronous motion. And yeah, as I mentioned, we're gonna focus on the undamped free vibration of two degree of freedom system. We will, from the equation of motion, we will derive it in a form, and then we will use the idea of the characteristic equation. What is the characteristic equation? What is the relationship between the characteristic equation and the equation of motion? And this is equation, and we can find a root of the characteristic equation. If you still remember something from ODE class, the root of the characteristic equation is eigenvalue. But in the vibration problem, eigenvalue has relationship to the natural frequency of system. So today we will learn about this. And once we obtain the eigenvalue, and we try to compose a vector that we call eigenvector. The eigenvector also can be related to the vibration problem. It will give some information about how the degree of freedom in the vibration problem change relatively to another degree of freedom. And this will be the concept of the mode of the shape. And yeah, we will try to solve until we get general response of two degree of freedom system. And we have one example, which is the simplified model of suspension system, and simplify into two degree of freedom system. And yeah, here today content. So yeah, we are going to review the equation of motion of two degree of freedom system. The our problem is a simple problem that we have a string, have a mass m, connect to a mass 2m, and spring, and a wall. And the three spring has the same stiffness. And the generalized coordinate for the mass m is x1, and generalized coordinate to the mass 2m is x2. The idea, here is just the review how to obtain the equation of motion. The idea is we need to assume that x1 is more than x2, so that we can expect the direction of the force in the spring between the two mass. What happened when x1 is more than x2? What happened to the mass m? Yeah, the mass m will have the normal force, will have the mg, but we consider the motion in the horizontal plane. So when the mass m travel to the right hand side with the coordinate x1, we will have force due to the spring to the left hand side, and the magnitude of the force will be the spring constant multiplied by the displacement x1. And we also have the spring here at this interface, at this connection. But we assume that x1 travel with a bigger distance than x2. So in this condition, the spring is under compression, which means the force here also resists the motion because x1 is bigger than x2. So the spring force is, the direction of the spring force is to the left hand side, is toward the left hand, to the left side. So the spring force will equal to the spring constant multiplied by the relative displacement x1 minus x2. Because x1 is assumed to be bigger than x2. How about the mass 2m? The mass 2m. Yeah, we have 2mg and have the normal force, and the action and reaction force of the spring force will push the mass to the right hand side. Does that make sense? The spring is under compression, and m1, no, the mass m is travel to the right hand side with a bigger displacement than x2, and the spring is under compression. So the force here, the direction of force, the force try to push the mass to the right hand side, and the magnitude of the force in the spring in the middle, the magnitude of the force are the same. It's just action and reaction force. How about this spring? If the mass 2 is travel to the right hand side, the spring is under compression, and the magnitude of the spring force is K multiplied by x2. So yeah, here is the free body diagram of these two mass. And the governing equation, the summation f x is equal to max. So if we consider the first mass m, the summation of mass is minus kx1 and plus, no, also minus kx1 minus x2 is equal to m x dot dot. X is x1 because we consider the mass, the displacement of the x1. And yeah, by rearranging the equation, what we have is mx1 dot dot plus 2kx1 and plus, no, minus kx2 equal to 0. How about the second, the mass 2m? If we check the mass 2m, again, summation fx equal to max. The force to the right hand side, k x1 minus x2, and the force to the left hand side minus k x2 equal to the mass 2m multiplied by the displacement, the acceleration of the x2. So again, we rearrange the equation to separate the terms. So we have 2m x2 dot dot and minus k x1 and plus 2kx2 equal to 0. If you pay attention to here, I try to separate the terms of the second time derivative of x1 and x1 and x2 in the order, because I'm going to write it in the metric form of x1 dot dot, x2 dot dot, and x1 and x2, and the force on the right hand side. Okay, from these two equation of motion of two generalized coordinates x1 and x2, if we want to write it in the form, in the one metric equation of multi-degree of freedom, yeah, we need to transform these two equations into the metric equation. So in the first equation, the component that multiply with the acceleration, this is like the metric of acceleration. This is like a metric of a displacement, and this is like a metric of input force. And what should be this metric and this metric? So by here, we simply put the coefficient into the metric. So m multiplied by x1 dot dot and nothing for the x2 dot dot in the first equation. And we have 2k that multiplied by x1. And we have, okay, and we have minus k. We have minus k that multiplied by x2, and the force is equal to 0 for the first equation. With the same idea, for the second equation, we have 2m that multiplied by x2 dot dot, but for the x1, the coefficient is 0. So we have 2m. And we have minus k. And we have minus k. And here we have 2k that multiplied by x2. And the force value also 0. So can you imagine what should be the name of this metric and this metric? So yeah, this is the inertia metric. And this is the stiffness metric. In some complicated system that we have the damping metric, yeah, the equation of motion may be written in the form of the inertia metric x dot dot when x is vector and plus c x dot and plus k metric x equal to f or the force metric. And yeah, the metric x is also time varying depend on the time t. And m is inertia metric. C is damping. And K is stiffness metric. Yeah, here is what we review for the equation of motion of second order system. Instead of separately write the two equation of motion, we have a way to combine it into a single equation, but it will be a metric in the metric form. If we increase the number of degree of freedom to maybe 3 degree of freedom, the dimension of the metric will change. Now the current dimension is 2 by 2. This is also 2 by 2. The vector for the position is 2 by 1. This is 2 by 2. And the force vector also 2 by 1. Yeah, but if we change the number of degree of freedom, the size of the metric will be n number of degree of freedom by n metric. The idea of synchronous motion, this idea is originate from observation. The observation, the simplified graphic for the observation is when we have two mass that connect to a spring and it vibrates. if the system is undamped system, the first phenomena that we can see is that the mass M1 and M2 that is deviate from the equilibrium point here. Both mass M1 and M2 will pass the equilibrium in the same time and reach this another point on the opposite direction at the same time, maybe the maximum point. But the the term synchronous, the meaning is it passed the equilibrium at the same time. Another possibility is the mass M1 and M2 it may arise the extreme condition here, and the M2 arrive the extreme condition here. And yeah, when this one vibrates back to equilibrium, this is also moved to equilibrium at the same time. So this means that the magnitude can be different. The magnitude can be different, and also the direction also different. But the coordinate of M1, the coordinate of M1 is x1, and the coordinate of M2 is x2. X1 and x2 can have different in magnitude, but yeah, it has the same frequency of vibration, and the phase shift also be 0 or 180 degrees, but cannot have different phase shift because it passed the equilibrium at the same time. So we can say it has the synchronous motion, means no phase difference, means x1t. If x1t is A1 sine omega t plus a phase angle. If x1 is A1 sine omega t plus phase angle, x2, this is x1, x2 can have a difference in the magnitude, but the vibration has the same in the phase. So yeah, as I mentioned, no phase difference means it can be 0 or 180 degrees. But if we write these two equations have the same phase shift, if the phase shift is 180 degrees of the difference, it just appears in the different side of the A1 and A2, which means A1 and A2 can be both the positive and negative one. If A1 is positive and A2 is negative, it may show the response like this. And one is positive, one is negative, but the phase angle here is the same. And the frequency is the same. Here is the meaning of synchronous motion. Yeah, instead of writing in the form of psi function, it's also true to write down in the terms of complex exponential. No. X2 okay, the symbol for the phase be the same. Yes, this is also true. So how this idea is important? This one is come from observation. And from observation, we know that if x1 is a1 psi omega t plus phase angle, x2 should be another magnitude multiplied by the same sinusoidal function. So by this knowledge, if you still remember the equation of motion, we're gonna apply this assumption on the equation of motion. Okay, when we rewrite the equation of motion, in the equation of motion we have m to m 0 0 and x1 dot dot x2 dot dot. And for the stiffness 2k 2k minus k minus k k minus k and minus k and multiply by the displacement metric equal to 0. And by this knowledge, we assume x1 equal to a1 psi omega t plus big phase, and assume x2 have different magnitude but same function. Okay, so if we know x1, what should be x dot dot? Do you have any idea to compose the metric that have only x1 and x2 in the vector? By this knowledge, we know that if we take second time derivative of the x1, the second time derivative of x1, what we have is t minus omega square a1 psi omega t plus the phase angle. In the same way, if we derive the second time derivative of the x2, we also have minus omega square A2 and sine omega t plus the phase angle. But this is x1 and this is x2. So now, yeah, we can combine these two metrics by multiply the first metric by the minus omega square. So to combine the metric, it seems like we still keep the metric of the stiffness and subtract by omega square multiplied by the mass metric. So yeah, we still keep the thickness metric, but the mass metric is multiplied by minus omega square. So this will be minus omega square m. The second component still be the same because in the mass metric is 0. How about here? The stiffness metric still be minus k, but the mass metric is 0. Here, the stiffness metric is 2k, and the mass metric multiplied by minus omega square will be 2 omega square m. And yeah, now we have the metric equation like here, 0 metric. So the characteristic equation, how can this equation always true? The characteristic equation is the determinant of this metric. The determinant of this metric is equal to 0. This will always make this equation become true. So yeah, the characteristic equation is this one. The determinant is a scalar, it's not a vector anymore. So the 0 is a scalar value. So how can we obtain the determinant of this metric? The determinant of this metric. The determinant, if you remember, if you multiply it downward, is positive, and if you multiply it upward, it's negative. So yeah, if the metric have A, B, C, D, the determinant is equal to A, D subtract by BC. So the determinant of this metric will be we need to multiply these two terms. So what we have is the determinant of the the metric, the determinant of the metric k subtract by omega square m is the determinant of 2k subtract omega square m and 2k subtract 2 omega square m and minus k and minus k. Okay, we need to find the product of these two terms. So we have 4k squared subtract by 4k omega square m and 2k omega square m and 2 omega power 4 m square. Is that correct? Yeah, and yes, thank you. And yeah, we subtract by k squared by multiplying it in diagonal upward. And this will equal to 0 because the determinant equal to 0 is the characteristic equation. Yeah, let's combine the terms. We have the terms of omega power 4 and the terms of omega power 2 and the terms that we don't have omega. So we have 2m squared omega power 4 and subtract by 6m k omega power 2 and plus 3k squared, and yeah, it's equal to 0. Do you have any idea how to obtain the omega from here? From the quadratic root? Yeah, before that, let's make it more easy. If we divide everything by 2m squared, if we divide all the terms by 2m squared, what we have is 3k per m and omega squared and 3k per m squared and per 2 equal to 0. Okay, the omega now is omega squared. By the quadratic root, the omega square should equal to by the quadratic root omega square should equal to this one square minus 4ac. 4ac means 6k squared divided by m squared, and all of this divided by 2. So it's equal to omega squared equal to all the term has k per m, right? and inside here will be square root 3 and divide by 2 of k per m. Now it seems like the omega square can be these two possible value. How about the omega? This is omega square. So if we want to find omega, actually we should have 4 possible value of omega, right? Because omega square can be 3 plus square root 3 per 2 and can be 3 minus square root 3 per 2. The omega square can be 2 value, and for each omega square, if we obtain only the omega, we can have the positive and negative root. But yeah, by the physical meaning, the natural frequency, the frequency can only be the positive value. So omega can be the square root. In general, omega can be the plus and minus square root of 3 plus minus square root 3 per 2 and k divided by m. And another set of omega can be plus and minus. Oh, I'm sorry. This can be just the first one. And the second one of the omega can be 3 minus square root 3 per 2 of k divided by m. But luckily that by the physical meaning, the omega can only be the positive value. So finally, we will have just one omega for each equation. So totally we have 2 omega. And with this one is square root. If you use calculator, it should be maybe, and this should be and yeah, the natural frequency. Finally, we have 2 natural frequency. The first one have the smaller value. The first mode of vibration, the first natural frequency, omega 1, and this is omega 2. The first one is smaller. So until now, in this slide, from our equation of motion, by using this assumption from the observation, we can compose the metric equation. And the characteristic equation in the scalar form is obtained through the determinant and the root of the characteristic equation. The root of characteristic equation the root of characteristic equation are the eigenvalue And in this case, we found that the eigenvalue here, luckily be the natural frequency. We have omega 1 and omega 2. And yeah, omega 1 always less than the omega 2. By the root, you have two omega 1 and omega 2. But yeah, by our definition of the mode of the natural frequency, omega 1 always less than the omega 2. And this is the omega 1 and omega 2, which is related to the k per m, the square root k per m. So yeah, the concept of the eigenvalue and natural frequency is this one. Is in this slide is related to the characteristic equation. So what next? We have the eigenvalue here, which is the natural frequency. The next topic is eigenvector and the mode of the vibration, the amplitude ratio. From if we go back to this equation, I will rewrite this equation again. The equation is the metric k subtract by omega square of the inertia metric equal to 0. So the metric of the k is this one. This is the inertia metric. So we just want to rewrite this metric. So it will be 2k subtract by omega square m and 2k subtract by 2 omega square m and minus k and minus k. And yeah, x1 and x2 is a1 sine omega t plus b and a2 sine omega t plus b. Okay, in this slide, oh no, I should write this here. Okay, let's write it again here. I'm sorry. I'm not sure I can just copy. I don't want to write it. So why not we what? Okay, so we don't know the value of the psi function, but by this metric equation, we can compose two scalar equation. The first scalar equation is composed from 2k subtract by omega square m and multiply by a1 and minus k a2 is equal to 0. Yeah, in this case, a1 and a2 multiply by the same function, the psi function. And yeah, if we divide it throughout the equation, finally, this equation is true. So by this equation, we can find the ratio of the a1 per a2. a1 per a2 is equal to k divided by 2k subtract by omega square m. What if we do the same way to the second row? If we multiply this to this, we have minus k a1 and multiply by the sine, and we plus 2k subtract by 2 omega square m and multiply by a2 is equal to 0. And yeah, this is also multiplied by the psi function, but the psi function is the same. So we also can obtain a1 per a2 by the ratio a1 per a2 by the ratio of the 2k subtract by 2 omega square m divided by k. These two equations, it should be equal. Although you write it in the different form, but the value should be the same, exactly the same. So you can select the equation 1 or you can select the equation 2 to continue, but the value will be the same. And the meaning of this is the amplitude ratio. Which is the ratio of the amplitude 1 per amplitude 2. The amplitude ratio that corresponds to the mode 1 is equal to k divided by 2k subtract by omega square m. When omega equal to the first mode of the natural frequency, the first mode of the natural frequency is this one, 0.634 k per m. Uh, 634 k per m. This is the first mode when the omega equal to the first natural frequency. We still use the same equation for the mode 2. Same equation means we still use k divided by 2k subtract by omega square m. But for the second mode, the omega equal to the second natural frequency. The second natural frequency is square root 2.366 K per m. So 2.366 this is the second mode. So if you see in both mode we use the same equation. Now I use the equation 1. You may also can use the equation 2. And it will give the same value when you put the omega 1 and when you put the omega 2. The mode 1 and the mode 2, the meaning is you use omega 1 or you use omega 2. It doesn't mean it comes from equation 1 or equation 2, because equation 1 and equation 2 always give the equal value if you put the omega equal to the natural frequency. So you can select just only one. Select this or select this, just only one. But you should put the omega that you obtained from the previous step. And yeah, the omega is the natural frequency in the first mode and in the second mode. If we compute this by the calculator, for the first mode, if we compute it, you can see we have m, and we can cancel, and k also we cancel. And finally, the ratio of the magnitude will be 0.731. You may check it if you have the same value as I have, if you have time. In the second case, if you use calculator, also you will have minus 2.73. So what is the meaning of this this ratio? This one we call the first mode shape, the mode shape. This one is the second mode shape. And yeah, the mode shape, the first mode shape or the ratio of the magnitude, it means that we have A1 per A2. It means A1 will be like 0.731 when A2 is equal to 1. And the second mode shape, in the second mode shape, if the A2 is equal to 1, A1 will equal to minus 2.73 here. In the first mode shape means when the frequency is equal to the first natural frequency, the magnitude, the ratio of magnitude is this one. So if we just assume A2 equal to 1, so A1 will be this value. The second mode shape happens at the second natural frequency. If we assume A2 equal to 1, the A1 will be minus 2.73. So what is the physical meaning of this? The physical meaning is if the magnitude A2 is equal to 1, A1 will be in the same direction, but smaller in magnitude. This is the meaning of this case. Go into the same direction, but A1 is smaller in magnitude. How about this one? The physical meaning is if A2 is equal to 1, if A2 is equal to 1, A1 will be in the opposite direction with a bigger in the magnitude. But yeah, by the idea, when it, when it moves to the equilibrium, it will pass the equilibrium at the same time. This one also, it will come back to here and pass the equilibrium at the same time. Here it's just the ratio of the amplitude. But we can see, like, yeah, if the system is vibrate at the first natural frequency, we will see only the effect of this. If the system is vibrate at the second natural frequency, we will see only this vibration. But in the normal case, when the system vibrates at one frequency that's not equal to the natural frequency, the total response of the vibration will be the combination of the effect of these two cases. So how can we write down into equation of the general response? So yeah, the free vibration will contain the result from both modes. In the same time. So, which means the response x1 and x2, the response, it contains the both mode, means the first mode, the ratio is and the second mode means this one. But the effect, how dominant of the first mode or dominant of the second mode will depend on the coefficient C1 and C2. That we still don't know the value of the coefficient. So the idea is that in any time in the free vibration, it will contain the effect of the first the amplitude ratio, and also the effect of the second amplitude ratio. And the first amplitude ratio will happen correspond to the first natural frequency. The second amplitude ratio it corresponds to the second mode of the natural frequency. So if you see here, this is the first amplitude ratio. This is the second amplitude ratio. And it corresponds to the first natural frequency. And this is the second natural frequency. The phase shift, the phase shift here can be different. But if you see here, it seems like we have 4 unknown. We don't know C1, we don't know C2, and we don't know the phase shift 1 and the phase shift 2. We have 4 unknown. The idea how to obtain all the unknown is depend on the initial condition. It means x1 and x2 at time 0, and also x1 dot and x2 dot at time 0. I will show two examples that correspond to the initial condition, so that you can get the idea. But let's imagine that the initial velocity is equal to 0. Let's assume that the initial velocity is equal to 0. And if you move x1 and x2 to the same direction, that's similar to the mode 1. If x1 and x2 are in the same direction, when we solve the equation, we will obtain the value of C1, C2, and the phase shift. If the initial condition is close to the first amplitude ratio, when we solve the equation, the value of C2 will close to 0, because the equation should be like in the in phase vibration of both two mass. But if you begin the motion by the initial condition that has opposite direction, when we solve the equation, C1 will close to 0, and we will have only C2. But in the real application, if we cannot make the initial condition close to this or close to this, we always find the value of the C1 and C2. But it's not easy to solve the equation. So the example is why not we give the x0, for example, equal to 4 and 2, and we give the x dot 0 equal to 0. With this, we can compose 4 equations. How can we compose 4 equations? The first equation is x0 equal to 2 and 4. X0 should equal to C1 multiplied by the amplitude ratio. And when time equal to 0, the sign of omega t is 0. So we will have only the phase shift. And for the second term, we will have the magnitude ratio and also when t is equal to 0, omega t is 0. So we will have only the phase shift. From this, we have two equations, right? The first equation is 2 equal to C1 multiplied by 0.731 and sine of this, and the second term. And the second equation is begin from like 4 equal to C1 multiplied by 1 multiplied by sine of phase shift, and C2, 1 and sine. How to use the initial velocity? To use the initial velocity, the idea is we need to obtain the first time derivative of this equation. But yeah, the first time derivative of this equation is not that complicated. We have the psi function of omega 1t. So by first time derivative, we just have the minus omega 1 multiplied by cosine omega 1t. No, not minus. Dip psi is equal to cosine. So yeah, by obtaining the first time derivative, we have omega 1 c1 and dip psi is cosine, right? And t equal to 0. And for the second term, it also has omega 2 multiplied by C2. And the magnitude ratio and multiplied by cosine of this. So now we have 4 equations. 2 equations from the initial position and 2 equations from the initial velocity. And we have 4 equations. And our unknowns are C1, C2, and sine and cosine. No, just only the phase shift. You can solve it by, yeah, we can solve this equation by the, like we know the sine and cosine relationship. And if you try to solve the equation, if you have time, the value when we solve the equation, if you have time, I may ask you to try to solve these 4 equations to obtain the value of the C1, C2, and the phase shift. But please don't worry. We have this chapter in our final exam, but I don't want you to spend the time in the exam room to solve the math equation to obtain this value. But I just want you to understand the concept. So to let you understand the concept, the exam question will similar to this question. Instead of using the complicated initial condition like this, in the exam room, I want you to try to understand this. What if we give the initial condition to be okay? We have the complicated equation here. Wow, I cannot copy, but the initial condition in the exam problem, we will give like this kind of initial condition. If you remember this equation, the general response of the second order system, x1 and x2, the general response will equal to C1 multiplied by the first mode of the magnitude ratio and C2 multiplied by the second mode of the magnitude ratio. And if I give the initial condition like this, you can just see by eye and don't need to solve the complicated equation. I want you to, our unknown is this 4 variable. If you see this initial condition by eye, I think you can expect that C1 should equal to 2, so that the equation is matched to the initial condition. So what should be the phase shift at time t equal to 0? How to make psi function of this become 0? So the phase shift should be 90 degrees or pi per 2, because psi of omega multiplied by 0 plus pi per 2 is equal to 1. And c is equal to 2, and multiply to this, it corresponds to the initial condition. How about C2? This initial condition is purely has no effect of the second amplitude ratio. So it's clear that C2 is 0. So when C2 is 0, we don't care what is the second phase shift. It can be anything, because the C2 is 0. So in this case, you don't need to solve the complicated equation, but you can look it by eye, and you can guess what is the value of the C1 and the phase shift. In exam question, I may give the initial position as, for example, uh, 5.46 and -2, for example. And yeah, please try this. How can we get C1, C2, and the phase that correspond to this initial condition? So yeah, the direct method to solve the equation is useful if the initial condition is different from the magnitude relationship. But in some case, if we exactly move the mass to the magnitude that correspond to the amplitude ratio, it's easy to obtain C1 and C2 by just consider the equation. Yeah, do you have any idea if we keep the initial condition to be like this? Yeah, you may compare it to this. And C2 may be equal to -2. And yeah, you need to know what should be the phase shift and what should be C1 and the phase shift that correspond to the mode 1. So the last example, should we continue? I mean, yeah, just let's continue for 5 minutes for the example, and then continue with the assignment and the terms project. The example also not difficult. I just want to give you a guideline, but I won't complete it in the class. You will do it by yourself. In this problem, we have a car, and we model the complicated suspension system as a 2-degree of freedom system. And the generalized coordinate that explain this system is just the vertical motion of the center of mass and the inclination of the vehicle body. And in the system, we have the spring without damper. So the problem is correspond to the undamped free vibration. And this is just the parameter in the model. So why not we give the mass of the car? We give the mass of the car and the moment of inertia. The moment of inertia about the, how to say, the lateral axis of the car. The moment of inertia for the pitch motion of the car. The pitch motion means, how to say, yeah, the pitch motion about this axis. So yeah, this is the pitch angle. So the moment of inertia is about the center of gravity for the pitch motion. Assume that the moment of inertia is mr squared. And the offset r, we may just assume it to be 1 meter. So it means that if the vehicle have the mass of 1,000 kilograms, the moment of inertia will be mr squared. And let's assume L1 maybe equal to 1 meter, L2 equal to 2 meter, and maybe K1 is equal to 40 kilo of Newton per meter. K2 is also have the same stiffness, 40 kilo Newton per meter. Today we learned about how to obtain the characteristic equation, the eigenvalue, and obtain the solution. But I think the difficult thing for you, and we need to review, is what we had learned in our early beginning of the class about the equation of motion. If we simplify, if we draw the free body diagram of the car that move with the displacement of x from the reference and have the inclination of theta in the clockwise direction. And from the equilibrium, if the car is pushed downward with the x in the distance, if it don't have inclination, the spring force, the displacement at this point, from equilibrium, if we consider the displacement, here should be x plus L2 theta, and here should be x minus L1 theta. Does that make sense? Because if the body of the car rotates with the pitch angle of the theta, the distance on the front of the car will be vertical displacement plus the displacement due to the pitch of the car. But for the rear view, it will be in the negative direction. The distance is smaller than x. So if we consider the spring force, if we remove the spring and just have only the spring force, the spring force will be k multiplied by the displacement. Here also k multiplied by the displacement. And our equation of motion from the first governing equation, summation f equal to max. So the summation of x is positive in the downward direction. So the spring force is in the upward, so it's negative. And also, I'm sorry, this is K1 and this is K2. Okay. And for the force in the front wheel, K2 multiplied by the displacement is also in the upward direction, so it's negative. And the x dot dot, the acceleration. So this is the first equation. The second equation is come from the summation of moment about the point C is equal to IC and alpha. And we assume alpha is positive in the clockwise direction. So the moment due to this force is in the clockwise direction. So it's the moment is the force multiplied by the moment arm. And the moment due to this force is in the counterclockwise direction. So it should be negative. And multiply by the moment arm. And it will equal to the moment of inertia multiplied by the second time derivative of the pitch angle. So from this equation, from all today's class, we know how to write the equation of motion in the metric form in the terms of the inertia metric and in the terms of the stiffness metric. In this case, the force metric, the force vector is equal to 0. And if you remember, our characteristic equation is the determinant of the stiffness metric subtract by omega square multiplied by the mass metric equal to 0. And by the root of the characteristic equation, you will have the natural frequency in the mode 1 and the mode 2. And yeah, how about the magnitude ratio? In this case, like the magnitude ratio is the ratio of the x1 divided by x2, the amplitude of A1 divided by the amplitude of A2. In this case, if the generalized coordinate, in this case, if our generalized coordinate is and the second generalized coordinate is the pitch angle. Oh, wow, I confused. Yeah, for the free vibration is in phase. So the omega are the same and the phase shift also are the same for both generalized coordinate. But the magnitude ratio in this case is A1 divided by A2, right? A1 divided by A2. But for this example, the magnitude ratio may be X divided by the theta. And the magnitude ratio will correspond to the first natural frequency, and the magnitude ratio that corresponds to the second natural frequency will be this one, the magnitude ratio 1, magnitude ratio 2. But the physical meaning of this magnitude ratio, in this case, the physical meaning of the magnitude ratio is how much the mass 1 is moved as relative to the mass 2. But in this example, the physical meaning of the magnitude ratio is what is the relationship between the vertical motion and the pitch angle? So if we have a big positive ratio, with a big magnitude, it means that if the car bump with a small angle, it will go with a big displacement. Small angle, but big displacement. But if this one is negative, for example, the meaning is if the car bump with a positive x, the angle should be negative. So this is the physical meaning of the magnitude ratio. If the magnitude ratio is positive, x is positive, and the pitch angle is positive. But if the magnitude ratio is negative, it means the side of the displacement and the pitch are in the opposite direction. If x is more than 0, if the car bumps downward, the pitch will make the front of the vehicle goes upward, bigger than the rear. Yeah, but if x is less than 0, if the car bump upward, if x is less than 0, yeah, the pitch angle may be bigger than 0. Is the physical meaning, depend on the sign of this. You need to derive and obtain the numerical value so that you can expand it with the physical meaning. So yeah, let's take time to check this example. And for the today content, now, yeah, it's done with the content. If you have any question, please let me know. And if we don't have question, we will go with the assignment 4 first. And after that, we will check the terms project. Okay, I may want to stop recording first and record it again for the assignment, okay?